Hello, 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 and welcome to Shiksha DaCosta. Today we're going to be modeling using quadratic relations. And this is part of the unit on connecting the graphs and equations of quadratic relations. So today we're going to learn the connections between a table of values and a graph, where the relationship between those two variables in the table is a quadratic relationship. You know you're successful at these skills when you can construct tables of values and graph the quadratic relations, as long as these are arising from real-world applications. And also when you can determine and interpret the values of the variables and what do they mean. If you're given a graph of the quadratic relation and that graph has come from a real-world application. To start off, let's think about board games. I'm a huge lover of board games myself. So in this particular board game, a player needs to place 3 soldiers to secure a square space on the board. With a reserve of 25 soldiers, can Patty, who is the player, secure 4 spaces? In this case, yeah, Patty has 25 soldiers, and if she needs 3 soldiers per space, if she divides this, then she'll end up with 8.333. So 8 remaining 1. So she can occupy 8 spaces in total. And of course, 4 is more than fine. She can occupy 8, and so she can definitely occupy less than that. She can occupy 4 if she wants to. Another way to think about this is 4 spaces that she wants to occupy times 3 soldiers per space means that she needs 12 soldiers to occupy 4 spaces. And of course, she has 25. So she has 13 soldiers more than she needs to occupy those 4 spaces. What if the spaces have to be arranged in a square themselves? So instead of getting a space here and another one over here and another one over here, what if the spaces need to be organized in a square? So obviously, and I'll invite you to copy down this table and complete it so you can see what sort of patterns emerge from this situation. So we know that if the side length of this square that she is trying to conquer is 1, that means that she only needs 1, 1, so she only needs 1 square. And we already know that to capture 1 square is 3 soldiers. So she will need, to capture 1 square, 3 soldiers. She'll need 3. So she can do that. But what if she wants more than just the 1 square? Well, she can't just capture another square all the way over here on this side of the board if she started here. She has to expand in a square. That means that she needs these pieces. So this is a square with a side length of 2. How many spaces is this in total? So one way to think about the number of spaces is the area of what she's trying to capture. Okay, so suppose this side length was 1 inch and 1 inch, then this would be 2 inches by 2 inches. So how many square inches is this area? That would be 1, 2, 3, 4 square inches. 2 times 2 is 4. So she would need 4 spaces captured. How many soldiers would that be? So this would be 4 spaces times 3 soldiers for each space is 12 soldiers that she needs. And she has 12 soldiers. She has 25, so she'll be fine. What about if she wants to expand even further, a side length of 3? So I'll invite you to pause this video right now and see if you can figure out how many spaces that would take up, or what is the area, and how many soldiers she would need to conquer all of those spaces. So hopefully that was enough time. We can see here that she wants to expand, but she has to expand in a square. So the side lengths of the square needs to go up by 1. So it'll be 3 by 3. And so the area of this square that she's trying to capture is going to be 9 spaces. 3 times 3 is 9 spaces. How many soldiers does she need for these 9 spaces? Well, if there's 3 soldiers for every space, then 9 times 3 gives us 27. Unfortunately, she can't do that. To be able to capture this, she needs 27 soldiers, but she's missing 2. She only has 25 in her reserve. So Patty is not able to get this far. She's not able to secure 9 spaces. In fact, the maximum number of spaces she could secure is 4. And that's because she only has 25 soldiers. Those extra 13 soldiers, well, they would go to waste if the spaces have to be arranged in a square themselves. So if you're ever thinking about like board game design or making your own board game and you want to include a mechanic that is sort of like this, where people can conquer spaces and they have to expand in a square, using this relationship, you would be able to know exactly how many soldiers to provide each player in their reserve. What if you are designing this board game and you say, okay, what about it? What if I just gave each player 150 soldiers? How many spaces would Patty be able to secure if she had 150 soldiers? So let's fill out this table. I'll give you a second to pause this video, copy down this table, and complete it to see if you can figure out how many soldiers are required for each side length. So hopefully you were able to pause and copy and fill out this table as best as you can. I'm going to take you through it now so you can see, if you didn't notice, that there are some patterns happening here. Notice that for the area, the number of spaces, we took the side length and we always multiplied it by itself. 2 times 2, 3 times 3. When you multiply something by itself 2 times, that's the same thing as squaring it, taking the number to the power of 2. So if I want to find out the space or the area, the number of spaces to conquer, I need to just take the side length and multiply it by itself, or just square it. So let's see if I can do that for all of these. To find the number of soldiers, then, if I know the number of spaces and each space requires 3 soldiers, I can just take the number of spaces, like I see here. The same pattern is happening, right? 4, I'm taking the number of spaces and I'm multiplying it by 3. 9 times 3. So this will be 16 times 3, or 48. So I can extend this pattern. 5 squared is 25. 25 times 3 is 75. 6 squared is 36. 36 times 3 is 108. 7 squared is 49. Times 3 is 147. And 8 squared is 64. Times 3 is 192. So I have filled out this entire table, and this will help me answer the question, how many spaces could Patty secure with 150 soldiers? It looks like she won't be able to secure 8 spaces, so I'll cancel that out. The most that she could secure is 7. Remember, the more important thing, other than, besides the fact that she's trying to find out how many soldiers she needs, is we are establishing that these patterns can help us solve problems. We are trying to examine here, what is the relationship between the side length and the number of soldiers needed? So if you did not know the side length, if I told you that this was the variable x, side length, how many soldiers would you need? So if you don't know what this number is, what are the operations that you will do to the letter x, or to whatever this number actually is? What operations will you do to find out how many soldiers you need? Take a second to pause this video and think about that and see if you can fill in these 2 spots on the table. Well, what I'll do is I will just follow the same pattern that I'm doing here. Whatever this number is, the first operation I did was I squared it. So I will take x and I will just square it. Whatever number that is, I will just square it. And then to find out how many soldiers I need, I will take this x squared, so because I took all of these numbers, and I multiplied it by 3. So I will end up with 3 times x squared. What are the second differences of this relationship? In other words, when we subtract, what is the difference between these? Those will tell you the first differences, and then we would subtract those to find the second differences. So I'll invite you to pause the video right now and see if you can figure out what this is. What are the second differences of this relation? Here are all the x values, and these are all the y values. So if you're having trouble with this, because first and second differences are a little bit tricky, let's take a look at how much you need to add to 3 to get to 12. What is the difference between 3 and 12? It's positive 9. 3 plus 9 gets us 12. These are the first differences, and we would have to do this for every single pair of y values. So this would be, or this every single pair of the dependent variable. So 12 to 27 means we're adding 15. 27 to 48 means we're adding 21. 48 to 75 means we're adding 27. 75 to 108 means we're adding 33. How am I getting these numbers? All I'm doing is I'm subtracting these two. So 147 minus 108 is 39. 192 minus 147 is 45. So these are the first differences. These are the differences, and because we've only subtracted it once, it is the first ones. I'm asking you for the second differences. So if you had trouble with this, now you know how to find the first differences. Can I ask you to pause the video right now and go ahead and see if you can figure out what the second differences are of this relation? So let's take a look at this. So second differences means we just have to subtract the first differences. 15 minus 9, that's 6. So 9 plus 6 got us 15. 15 plus 6 would have got us 21. 21 plus 6 gets us 27. Plus 6 gets us 33. Plus 6 gets us 39. Plus 6 gets us 45. Look at that. The second differences are constant. They are always the same. And they are at constant at exactly 6. So let's try graphing this relationship now. We know that it has constant second differences. All the second differences are 6. Let's see what this looks like on a graph. So here you can see I've started by sketching out a grid, a Cartesian coordinate plane. Notice my x values, they go from 0 to 8. And I know that this is okay. Actually, they go to 9. I know that this is okay because all of my independent variable, the side length, which I will put at the bottom here, those numbers only go from 1 to 8. And the number of soldiers that I need, those numbers go from 3 all the way to 192. So my y-axis, my vertical axis, this is where I will plot how many soldiers I need. That needs to have space for all the way up to the number 192. This is a really critical piece in graphing relations. You need to make sure when you are sketching out a graph, your x and y axes, they have enough space to contain all of the points that you have here, all of the points in your table of values. And I know that mine does. So let's start actually graphing it. I'm going to start off by placing 1 here at 0, 0. Because if I had a side length of 0, 0 squared would be 0, and 3 times 0 would also be 0. So I know that I would have a point that I don't have in my table of values would be 0, 0. Let's start plotting the points that I actually do have. So there's the first one, and this would be 1 on the side length, so it would be right here, and then 3 soldiers needed. So it would be a little bit higher than this. Okay, so just a little bit up, but because this is 25, notice 50 and half of that is 25, this point will still be really close to the x-axis. It's not very high up at all. Let's continue. 2 and 12. So there's 2 and up to 12. 12 is about halfway between 0 and 25. And then let's just keep going with that. 3 and 27. 4 and 48, so just below 50. 5 and 75. 6 and 108. 7 and 147. And 8 and 192. So I have plotted all of these points on this graph. Notice they all fit because I set myself up for success by making the axes really, really tailored to my table of values. So what is, if I were to try to connect the dots with a nice smooth curve, what would that look like? Notice it's not a straight line. If I were to connect these dots with a straight line, the line would sort of end up over here. But we can see that at 8, the points are much higher. So I would need a curve to graph this relation. This is a non-linear relation. So what is the relationship between side lengths and soldiers needed? So if you have a side length of x, you would need 3x squared soldiers. And this is what the graph of this relationship looks like. What we've done here is created a mathematical model. We have modeled a situation that is happening in real life using mathematics. In this case, real life is a game, but still real life. We play games in real life. On a graph, this relationship forms a very specific shape. That shape is called a parabola. And this relationship that we graphed only formed half of the parabola. The other half would look like this. Now, this would be for the spaces if the side length was a negative number. But that doesn't make any sense to calculate, right? So that's why we did not graph this half. We only started at 0. Actually, we started at 1. So because that doesn't make sense, we decided to ignore it. But if this relationship were to continue this way, this is the other half of a parabola. Parabolas are symmetrical, which means the left side and the right side are exactly the same, as if the middle, going right through the tip here, was a mirror. So if this was what you look like, and if you were looking at this mirror, this is what you would look like on the other side of the mirror. So that's what I mean by symmetrical. All quadratic graphs are parabolas. Whenever you graph a quadratic relationship, it will always form a parabola. How do you know if you have a quadratic relationship? Well, if you're looking at the algebraic expression of that relationship, you would see an x squared term. And this square is exactly why we call these relationships quadratics, because quadratum is Latin for the word square. So just to summarize, any relation that has constant second differences, and remember that our relation had constant second differences, the second difference was always 6. Any relation that has constant second differences is a quadratic relation. We call it quadratic from the Latin word quadratum, which means square. These are called quadratic or square relations because in the algebraic expression, you will see a term that has x squared. You will see something squared in the relation, in the expression itself. This means that the degree of the polynomial, and degree is basically the highest exponent on the variable, which is 2. The highest degree is 2. The shape, when we graph quadratic relations, they always create this shape called a parabola. And that makes them very interesting to us, or very easy to figure out a few very important features. The parabola kind of looks like a U shape, right? Although if we were to transform it, we could see that parabola upside down. So it'd actually be shaped kind of like an N. At the tip of the U, at the tip of the parabola, the point that is right there is called the vertex. If the parabola is in fact shaped like a U, then the y value of this vertex, the point that's here, you can see that this is going to be the lowest point of the graph. This will be the lowest possible y value. And that's why we call that the minimum. Minimum means the lowest, right? And if it's shaped like this, so if it's upside down, then the point would still be here at the tip, but notice that this point is at the very top. This is the highest possible y value, and that's why we call it the maximum. So the vertex always will tell you, the y value of the vertex will always tell you either the minimum or the maximum of the quadratic relation. It just depends whether it's shaped like a U or shaped up like a U that's upside down. So let's do a quick example of this. Find the vertex and the maximum or minimum of the quadratic relation graphed below. So here we can see that this is a parabola, right? It's shaped exactly like we expected it to. And this parabola has a vertex, and the vertex is right here at the tip, and that is at the coordinates of the vertex are 4 and 6. Okay, that's pretty good. What can I do with this information? Well, does this quadratic have a maximum or does it have a minimum? Because it is shaped like the upside down parabola, this is the highest point on the quadratic. Notice if I asked you, hey, for what x values is the quadratic equal to 2? You would say, okay, here's 2, and that would be about 1.5 and about 6.5. Okay, so we can get 2 for our y value. What if I said 4? Okay, that would be about 2.3 and about 5.7. Okay, what if I said 6? Okay, then there's only one point that has a y value of 6, and that is the x value of 4. And what if I said 7, 8, or any number above 6, even like 6.1? There are no points above that have a y value that is greater than 6. So 6, this is the maximum. The y value of the vertex, the maximum is 6. If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice questions, solutions, handouts, and more on our storefront. Thanks and have a great day.